In between stellar mass and supermassive black holes, a third category of black hole also exists, known as intermediate mass black hole, which ranges from 100 to 1 million solar mass. According to one theory, intermediate mass black holes started their journey as less massive stellar mass black holes. As time goes by, it consumes enough space matter to form intermediate mass black hole. Intermediate mass black hole, in short IMBH, continues its habit of eating and gobble up more matter as time passes. Depending upon the type of meal it consumes, sooner or later IMBH will get promoted to SMBH, which is short for supermassive black holes. The existence of intermediate mass black holes also demystifies the existence of supermassive black holes, as it proves supermassive black holes were not born supermassive, but it is the result of a long journey and various stages it undergoes from stellar to intermediate to supermassive. We find the existence of supermassive black holes surprising, as we only witness the final product and not the whole process that the universe architects for billions of years. Another theory suggests that IMBH is born due to the collapse of the extremely dense gaseous region directly to a black hole. The gaseous region must be extremely massive that instead of manufacturing a star, it caves in directly to an intermediate mass black hole. This theory makes IMBH a lot younger, as it skips the formation of a massive star, which takes millions of years to create a stellar mass black hole. Similar to supermassive black holes, IMBH is most likely to be found at the center of galaxies. For example, the nearest known Seyfert galaxy NGC 4395 has a central black hole with an estimated mass of 300,000 times that of the Sun. Another candidate for IMBH, having a mass of 20,000 Sun, lies at the center of a globular cluster known as Mayall II. Named after American astronomer Nicholas Mayall, this globular cluster is located 130,000 light years away from the nucleus of its parent galaxy, that is Andromeda. Strangely, an intermediate mass black hole is predicted at the center of galaxy RxJ1140.1 plus 0307, that is about the size of our Milky Way galaxy. Its central black hole mass is estimated to be less than a million solar mass, which is comparatively low and falls under the category of IMBH. The ultra-luminous X-ray source M82-X1 is another IMBH contender, found 11.42 million light years away in M82, also known as Messier 82, also known as Cigar galaxy. Its calculated mass varies from roughly 100 to 1000 solar mass. HLX1, short for Hyperluminous X-ray Source 1, is another applicant for the IMBH job. It is located 290 million light years away at the outskirts of the lenticular galaxy ESO 243-49. Situated away from the galactic plane, this IMBH aspirant was probably a central black hole of some dwarf galaxy, which is merged into the large ESO 243-49 galaxy. This violent event may have thrown the central black hole of the dwarf galaxy away from the galactic plane. In order to search for an intermediate mass black hole, we actually don't have to look that far, as strong evidence points out IMBH existence in our own Milky Way galaxy. In 2004, an intermediate mass black hole candidate termed as GCIRS 13e was found orbiting very close to Sagittarius A star, that is only 3 light years away. Recent studies found that it is surrounded by a cluster of 19 objects. Out of 19, 15 are found to be dense gaseous regions, and the other 4 are massive stars. The speed of these bodies indicates the possibility of intermediate mass black hole that holds the mass of 1300 suns. Recent discoveries suggest that an intermediate mass black hole may be residing in interstellar gas cloud XCN 0.009-0044 that is found only 25 light years away from Sagittarius A star. The cloud is roughly 3 light years in diameter, and the proposed IMBH mass is calculated to be equivalent to 32,000 suns. The name XCN denotes the presence of hydrogen cyanide gas in the cloud. When two black holes collide and merge to form a single black hole, some mass is converted into gravitational waves. The ripples of gravitational waves, when passed through the Earth, are detected by the LIGO and Virgo detectors situated in the United States. These detectors identify several neutron stars and black holes by detecting their gravitational waves caused by their collision. In 2016, LIGO and Virgo detected ripples of gravitational waves that were coming from 1.3 billion light years away, generated by the collision of two black holes. The masses of both black holes were 36 and 29 solar mass respectively. After the collision, the resulting black hole constitutes the mass of 62 solar mass, as it loses 3 solar mass in producing gravitational waves. Another gravitational wave caused by the merger of black holes was detected and designated ZW190521. Black holes that collided had a mass of 66 and 85 times the Sun, which after the merger create a single intermediate mass black hole with a mass of 142 suns. The remaining mass of 9 suns were lost in the explosion and converted into ripples of gravitational waves, which takes more than 7 billion years to reach on Earth. It is astounding to know that the gravitational waves were coming towards the Earth before the Earth was even born. Everything falls into place from the evolution of Earth to humans to LIGO and Virgo detectors at the right time to detect this cosmic event which happens more than 7 billion light years ago.